Good morning everyone. In this video, we are going to study about the interfacing memory devices concept. Interfacing the memory devices concept. Under the memory devices, we are going to study about the different types of memory devices. One is a ROM and another one is a RAM. One is a ROM, another one is a RAM. Okay now. So what exactly the ROM device? ROM device is called as a permanent memory. The ROM memory device is called as a permanent memory. Okay now. Permanent memory means the data which is stored inside the ROM device is going to be retained even we turn off the power supply applied to the ROM device. Even we turn off the power supply to the ROM device, the data which is stored in the ROM device is going to be retained. Retained means we are not losing the data even we turn off the power supply applied to the ROM device. Okay now. So that's why the ROM memory devices are called as a non-volatile memories. The ROM memory devices are called as a non-volatile memory. Non-volatile memory. Non-volatile memory. And it is one of the important question for your competitive exams. If you are going to write any competitive exams and other that you are having the microprocessor concept, obviously the non-volatile, or you may get the question as which memory device is a non-volatile memory. So you try to remember this one. ROM device is called as a non-volatile memory. Okay, ROM device is called as a non-volatile memory. So when we are taking the memory device, obviously we are having the address lines as well as the data lines. Let us see. What we do is to try to note down the points related to this one. ROM device is nothing but it's a permanent memory, and it is called as a non-volatile memory. We are going to see the diagram for the ROM device. So here I didn't prepare the slide for this one. I'm just taking the scanned copies from your textbook. Okay, so here in this part, this is a ROM device, ma. This is a ROM device. In this particular ROM device, I'm assuming that the number of address lines which are there in this particular ROM device is a A0 to A14, means total 15 address lines are there and 8 data lines are there. So 15 address lines means we can able to access the 2 per 15 memory locations. That is this particular memory, this particular device is having the 2 per 15 memory locations. 2 per 15 memory locations means in short it is going to be the 32 KB. Okay now. So in short it is a 32 kilobytes of memory. So this particular ROM is having the 32 kilobytes of memory. So 32 kilobytes of memory means 32 kilo locations are there and each location is able to hold the 8-bit information. So here we are having the two more control signals for this particular ROM device. One is a output enable signal. One is a output enable signal. Another one is a chip enable signal. Another one is a chip enable signal. So output enable signal is nothing but if you want to read the data from this particular ROM device, you are supposed to apply the output enable signal along with the chip enable signal. If you are not enabling these two control signals, then you can't read the data from the ROM device. So ROM is having the ROM is a read-only memory. We can read the information from the ROM device. We can't write the information into the ROM device. Why? Because the data which is stored inside the ROM is going to be burned by the manufacturer during the manufacturing time. During the manufacturing time. Means the user who is going to use the ROM device is unable to change the values or the program which is there in the ROM device. This is the problem in the initial days. So whenever you want to change, if you want to change the data available in the ROM device, you are supposed to give your specific information to the manufacturer so that during the manufacturing time itself, they are going to burn your program into the ROM device. So in order to avoid this conflict, means visiting, preparing the program and giving that information to the manufacturer is a little bit difficult. So that's why what they have done is they have introduced one more type of ROM device. They have introduced one more type of ROM device, that is nothing but the PROM device. So ROM is the first one, and the next one is a PROM device, which is a programmable read-only memory. Programmable read-only memory. In this one is also the permanent memory, but the advantage of this PROM over the ROM is nothing but here the manufacturer is allowing the user to change the program available in the PROM memory for one time. For one time means only one time the user can change the program available inside the ROM as per his requirement, but once he burn the data, then obviously means there is no second chance for the user or the programmer who wants to change the program available in the PROM memory device. There is no second chance. So only one time you are allowed to change the data. again there is a drawback. Okay, now because only one time now, so to overcome that one, they have introduced one more kind of PROM device. I'm not giving the elaborated explanation for individual one, I'm just giving the overview. So in order to avoid the problem which is there in the one time writing info, one time writing problem in the PROM, they have introduced one more thing called as a EPROM. EPROM is nothing but the erasable programmable read-only memory. So means here how many times the programmer or the developer wants to change the content available in the ROM device, that many times they can change. But there is again one more drawback, which is nothing but every time you are supposed to remove the EEPROM from the integrated part and place that one in the specific program burner IC, specific program burner device, and burn your data and remove that one again. I insert that one in the original place. There is a little bit difficult in the EEPROM device also. Means every time you are supposed to remove that data, and if you want to burn your program, there is a there is a separate device which is called as a program burner. Every time you are supposed to place that one in the program burner and load the information. So in order to avoid this problem also, they have introduced one more PROM device, one more memory device called as a EEPROM or E2 PROM. Simple case is the EEPROM or the E2 PROM. EEPROM is nothing but the electrically erasable programmable read-only memory. Electrically erasable programmable read-only memory. And this memory, using this particular memory, how many number of times the user wants to change the program, that many number of times the user can change the information available in this particular memory devices. Okay, in this particular memory device. And as we move on, they are called as a flash memory devices also. So this is about the ROM device. ROM device is nothing but, in brief, it is a permanent memory, and which is called as a non-volatile memory. Permanent memory is nothing but the data which is going to be stored in the ROM memory is not going to be loose even we turn off the power supply. Means it is going to be retained even we turn off the power supply. So that's the advantage of the ROM device. Next case is a RAM. Next case is a RAM. RAM is nothing but the random access memory, and it is called as a temporary memory. RAM is nothing but the random access memory. It is called as a temporary memory, and in technical format it is called as a volatile memory. It is called as a volatile memory. So depending on the construction, there are two types of RAM devices. One is a SRAM and another one is a DRAM. There are two types of RAM devices. One is a SRAM, another one is a DRAM. SRAM is nothing but the static RAM. DRAM is nothing but the dynamic RAM. SRAM is nothing but the static RAM. DRAM is nothing but the dynamic RAM. Let us go for the static RAM. Okay, now SRAM. Okay, now let us go for the static RAM. Okay, SRAM is nothing but the static RAM. SRAM. Okay, SRAM is nothing but the static RAM. This memory, this RAM device is designed with the help of the. It is designed with the help of the flip-flops. It is designed with the help of the flip-flops. It is designed with the help of the flip-flops. Advantage of the using the flip-flop is the speed of the execution is more, but the drawback is it is each flip-flop is taking the more space, and as it is taking the more space, the obviously cost of the IC is going to be changes. Okay, now the cost of the IC is going to be increases. That is a drawback. Advantage is speed of the device is very fast. Okay, now speed. Advantage is the speed, but the drawback is cost and cost and space. Okay, cost and space. So these are the drawbacks of the SRAM. Okay, now so static RAM devices are designed with the help of the flip-flops. Okay, now static RAM devices are designed with the help of the flip-flops. Okay, now the thing is yeah, the flip-flops, but the advantage is what, when you are using the flip-flops, the speed of the execution or the speed of the memory device is very fast. Okay, now and the cost is going to be increases as the space occupied by the flip-flop is increasing, then the cost of the system is going to be increases. And the drawback of one more drawback is there for the SRAM, which is nothing but the it is available during the olden days. As per our textbook, during the olden days, the static RAM size is very small in size, very small in size. It is around 128 KB. It is around 128 KB. So this is the size of the static RAM during the at the time of the program, at the time of the book written. Okay, but nowadays we are having the static RAM sizes in the megabytes also, in the MB sizes also. But this is what we are having the initial days. Okay, now so 128 KB of size means the small in size. SRAMs are the small in size because it is a cost effective one, as we are using the flip flops. So the next case is the DRAM. Next case is the DRAM. Okay, now DRAM is nothing but the dynamic memory, dynamic RAM. DRAM is nothing but the dynamic. Sorry, DRAM is nothing but the dynamic RAM. Dynamic RAM. And this DRAM is designed with the help of the capacitors. Sorry, the DRAM, right? This one is designed with the help of the. I'm sorry, I can't get back the previous information. So what you do is you go back and hold the give the pause button and note down the information. So DRAM is nothing but it is designed with the help of capacitors. It is designed with the help of capacitors. Okay, now advantage of using the capacitors is the space occupied by the capacitor is going is more sorry, the space occupied by the capacitor is very less compared to the flip flops. So that's why the size of the DRAM is more, means we are having the maximum capacity in the DRAMs compared to the SRAM, and as we are using the capacitors, the cost of the DRAM is also going to be less compared to the SRAM. Cost of the DRAM is also going to be less compared to the SRAM. And we have one more point regarding the SRAM. SRAMs are used in designing the cache memories. In designing the cache memories, SRAMs are used. What exactly the cache memory we will see as we move on in the, I think in the second unit we are going to see that one. So cache memory, in designing the cache memory we are using the SRAM. When you are going to purchase a laptop or your what we say, the smartphones also, better to cross check the how many levels of cache memories are there. So if we are having the more number of cache, more level of cache memories, and capacity of the cache memory is very high, then definitely you can go and purchase that particular device, because the execution speed is going to be increases. Your device execution speed is going to be increases. So let's come back to the DRAM. DRAM is designed with the help of the capacitors. DRAMs are designed with the help of the capacitors. Advantage of using the capacitors is it is occupying the less space compared to the DRAM, and obviously the cost of the DRAM is going to be less compared to the SRAM. But the drawback of this one is, as we are using the capacitors, we are having a problem in the capacitor, which is a discharge problem. Which is a discharge problem. We are having a problem called as a discharge problem, because the information which is stored in the memory is nothing but binary information. That binary information is stored in the capacitor in the form of the charge. So obviously we know one point regarding the capacitors, that they are unable to retain the information for long period of time, because there is a leakage problem in the capacitors. Okay, now there is a leakage problem in the capacitors. To overcome that particular leakage problem, what we are supposed to do is the DRAM should be refreshed periodically. The DRAM should be refreshed periodically. Refreshing is nothing but reading the information and write back the information in the same position. So as we are not having the board, I am unable to explain the in detail scenario how exactly it is performing, but we'll see the diagram. Okay, don't worry about it. So as we are having the discharge problem, we are supposed to refresh the DRAM periodically. Means for every 1 microsecond or 2 microseconds, or for every 1 milliseconds, depending on the type of the memory device. Depending on the memory device, we are supposed to refresh that particular DRAM periodically. Okay, now why we are supposed to do that one? Because the capacitor is having the discharge problem. It is having the leakage problem. Okay, now so it is having the leakage problem. Because of that, we are supposed to refresh that DRAM periodically. Let us go back to our diagram explanation. So this is a RAM, and uh, this RAM is a static RAM. This one is a static RAM, and this one is a what is that? Sorry. Yeah, this one is a static RAM. This one is a ROM device actually. Okay, now so let us go for the static RAM. In this diagram, we are having the 12 address lines. Means my RAM device is having the 12 address lines. So obviously 12 address lines means what is the maximum memory? That is what is the memory that can be accessible by using the address lines is 2k. Sorry, it is a 12 lines means 2 power 12. 2 part rule means obviously it is a 4K. It is going to be the 4K, and each memory location is able to hold the 8-bit information. As the data bus size is a 8-bit, so obviously each memory location is able to hold the 8-bit information. Here also we are having the 3 control signals. So in case of the ROM device, we are having only the 2 control signals because we can perform the read-only operation. We can perform the read-only operation. So that's why output enable signal is nothing but the read-only signal. Means from the microprocessor, inside the microprocessor we are having uh, two control signals. Na? One is a RD bar, one is a RD bar, and another one is a WR bar. Another one is a WR bar. In this case, so I'm not. Let me show you the bar also. Okay. So RD bar and the WR bar. RD bar and the WR bar. Okay. So here the output enable signal of the ROM device when you are trying to interface this one to the 8086 microprocessor. This is the 8086 microprocessor, no? Processor. So when you would like to interface this particular ROM device to the microprocessor, you are supposed to connect the output enable signal of your ROM device to the read signal of your microprocessor, because we are able to perform only the read operation from the ROM device. We are able to perform only the read operation from the ROM device. Now, what about the chip enable signal? So here, when as I told you during the explanation of the address decoders, interfacing the memory devices to the microprocessor is nothing but mapping the memory devices into the memory space provided by the microprocessor. So that is going to be done by the address decoder. So the chip enable signal is connected to one of the output of the address decoder. That may be the 74LS138, that may be the 74LS139, or we are having the PLDs also. Now using any one of the address decoder, the output of one of the output of the address decoder is connected to the chip enable signal of the ROM device. Chip enable signal of the ROM device. How we are going to interface these devices, we will see as we move on. So don't worry about it. Okay. So now when you are going to study about the RAM device, we are able to perform the read operation as well as the write operation. RAM is the temporary memory. We can perform the read-write operation on the RAM device. Okay. So as we are having the read-write operation possibilities, there are 2 control signals to perform the read-write operations. One is the output enable signal, which is nothing but the read signal. Write enable signal, which is nothing but the write signal. Okay. So as usual, chip enable signal is there. Okay. This chip enable signal is connected again to the one of the address decoder, so that it is going to be mapping this memory device into the memory space. So here, this particular output enable signal of the RAM is connected to the read signal, and write signal is connected to the write signal is connected to the write signal of the RAM. Okay, now we compared to the ROM, we can perform the read operation as well as the write operation on the RAM device. And this chip enable signal is connected to the one of the output of the address decoder. We will see that part as we move on. Now, what we do is we'll go to the DRAM now. So we are studying about the DRAM, right? We are studying about the DRAM. So what is the drawback of the DRAM? Drawback of the DRAM is we are supposed to refresh the DRAM periodically. We are supposed to refresh the DRAM periodically. Why we are supposed to refresh the DRAM periodically? Because the DRAM is constructed with the help of the capacitors. So here we are having the structure, internal structure of the DRAM. We are having the internal structure of the DRAM along with the refreshing operation also, which is not shown over here. So here, whatever the memory device in this structure, in this particular interfacing diagram, we are having the multiplexed address. Multiplexed address in the sense, how many number of address lines are there for this particular DRAM? How many number of address lines are there for this particular DRAM? That particular those address lines are those address lines are divided into 2 groups. One is the row address and another one is the column address. Divided into 2 groups. One is the row address and the another one is the column address. Let us suppose I'm having the 12 address lines. So obviously it is going to start 12 address lines means let me take the 16. It is a better number. Okay. A16 to 16 address lines means A15 to A sorry A15 to A8, A7 to A0. So total 15 address lines are there. Na? 16 address lines are there. Na? These address lines are equally grouped into 2 parts. These address lines are equally grouped into 2 parts. So as we know that it is a higher order address bus and it is going to be the lower order address bus. One is a higher order address bus, another one is a lower order address bus. the first half of the higher order address bus is called as a row address. The first half of the higher order address bus is called as a row address, and second half of the address is called as a column address. First half of the bus is called as a higher order bus or the row address, and the second half is called as a lower order bus or the column address. Lower order bus or the column address. Okay. No? So here I'm going to take, in order to access this particular DRAM, I'm not taking the entire what is that 16-bit address. Actually, this is 16-bit address split into two parts now. So I'm going to use only the 8-bit address. I'm going to use only the 8-bit address bus in this diagram. So first, in order to access a particular memory, or in order to refresh a particular memory, because the DRAM should be refreshed periodically. Na? In order to refresh the memory, or in order to write the information into the memory, the address is split into two parts. One is a row address. Sorry, I'm sorry. I'm sorry. No, wait a minute. No. So here we are having the address now. So the entire address is split into two parts. I'm assuming that it is a 16-bit address bus. It is a 16-bit address bus. A15 to A8, A7 to A0, A7 to A0, A7 to A0. Okay. So the higher order byte is called as a row address. Higher order byte is called as a row address, and lower order byte is called as a lower order byte of the address bus is called as a column address. This one is a row address, this one is a column address. Now, if you want to write the information or if you want to refresh the DRAM memory, what you are supposed to do means, first of all, you are supposed to place the higher order. We are supposed to place the higher order address. We are supposed to place the higher order address bus address on the address bus, and generates the row address strobe signal. Okay, now, when you want to perform the write operation or when you want to perform the refresh operation, the method which is followed by the DRAM is, if you want to write the information into the memory or if you want to perform the refreshing operation, first you are supposed to place the row address. Row address is nothing but the higher order address on the address bus, and it generates the row address strobe signal, which is the RAS signal. Okay, now row address strobe signal. So when you are generating the row address strobe signal, the address which is there on the address bus, the address which is there on this particular address bus, before generating the RAS, it is commonly available to this particular device as well as to this particular device. But as we are enabling the row address strobe signal, then this latch is going to be receives the information. This latch is going to be receives the information from the address bus, and this latch is going to be disabled because we are not enabling the CAS signal. We just enable the RAS signal. And after some time, after enabling the latch signal, with the help of the RAS, which is a row address strobe signal, the information is going to be further moved into the ROM decoder. As we know that the decoders are going to be map the memory device. Now decoders are going to be map the memory devices. They are going to be enable the rows, or in simple format I can say that the memory is going to be looked by the microprocessor in the form of the matrix format. Simple statement. Okay, in the form of the matrix format. After placing the what is that higher order address on the address bus and generating the RA signal, this latch is going to be enabled. And in the second case, means in the second cycle, it is going to be places the lower order address on the address bus and generates the CA signal and disables the RA signal. Because of that, this address, whatever the lower order address is there, which we call it as a column address, is going to be latched into the device, and it is going to be given as an input to the column decoder. Now, as we are having the row address as well as the column address, depending on the control signal, write enable signal or whatever it is, depending on the control signal, the microprocessor is going to be performs the means the microprocessor giving the instructions by using one of the control signal, and depending on the control signal, the DRAM is going to be performs the memory write operation or the memory read operation, or it is going to be perform the refreshing operation also. It is going to be perform the memory refreshing operation. So refreshing is going to be done with the help of the row and column format. Means when the DRAM is trying to refresh, the memory is going to be looked in the matrix format. We are having the row address format as well as the column address. So means we by enabling how the memory is going to be refreshed is the question. Na? So I'll give one statement. Don't get confused. In simple short, we may use the row addresses to enable the memories, whatever the memory locations which are there in that particular row, all the memories are going to be enabled. Or we may use the column addresses to enable, in the sense it is going to be refreshed. In order to perform the refresh operation, we may use the column addresses. So whatever the memory locations are there, we under that particular column, all those memory locations are going to be refreshed. So this is the DRAM refresh operation. It is a DRAM refresh operation. So when the DRAM is performing the refresh operation, the memory that is a address is split into two types. One is a row address and another one is a column address. Row address and the column address. So this is about the memory devices. Okay now. So there are two types of memory devices. One is a ROM device, another one is a RAM device. ROM device is nothing but the read-only memory. ROM device is nothing but the read-only memory. RAM device is nothing but the random access memory. So RAM device is further divided into two types. One is a static RAM, another one is a dynamic RAM. Static RAM is nothing but the SRAM. Static RAM is nothing but it is designed with the help of the flip-flops, and the drawback of the static RAM is cost effective one, and advantage is the speed is more compared to the DRAM. DRAM is designed with the help of the capacitors. The drawback of the DRAM is leakage problem. As we are using the capacitors in designing the DRAM, the capacitors are having the leakage problem. Means they are unable to hold the charge for long period of time. So because of that, we are supposed to refresh the DRAM periodically. But the advantage of the DRAM is the size of the DRAM is very high more. It is in the megabyte size. It is in the megabyte size, but during static RAM is in the kilobytes during the initial days. This is the explanation during the initial days. Now let me tell you one important point. It is not related to this whatever the memory devices concept we are having. I just want you to know how exactly the memory devices are going to be designed. I'm just concentrating on one memory location now. Each memory location is able to hold the 8-bit information. So assume that we are having the 8 bits. We are having the 8 bits. Okay. I'm assuming that it is the most significant bit position, and this one is the least significant bit position. Man, why you are doing the mistakes? Okay, I'm sorry. I'm having the memory device now. I'm having the memory device. Each memory location is able to hold the 8-bit information like that we are seeing now. I'm not considering all the bits, I'm considering only the few bits. Same thing is going to be applicable for the rest of the bits. Okay. So I'm assuming that this is a D7 most significant bit. This is the next bit position. And this one is going to be the least significant bit. This is the DG. Whatever the bit positions we are having now, I told you that static RAM designed using the flip-flop, dynamic RAM is designed using the capacitors, right? Each how many number of bits are there in each memory location? 8-bit information. Each memory location is able to hold the 8-bit information. Now I'm just taking only one memory location, so which is holding the 8-bit information. Each bit is called as a cell. Each bit is called as a cell. Okay, and each cell is designed with the help of the flip-flop. If it is a static RAM, which is a SRAM, then each cell is designed with the help of the flip-flop. FF. Each cell is designed with the help of the flip-flops. Means in order to hold the 8-bit information, how many flip-flops are there? 8 flip-flops are there. Are we clear? Okay. So each bit in the memory location is called as a cell, and each cell is designed with the help of the flip-flops in the static RAM. So in order to hold the 8-bit information, these flip-flops are interconnected in such a way that they are able to hold the 8-bit information. Means in order to hold the 8-bit information, we are supposed to concatenate the flip-flops in such a way that they are able to hold the 8-bit information. 8-bit information. If we are using the capacitors in the DRAM, obviously each location, each bit is called as a cell, and each bit is designed with the help of the capacitor. Means 8 capacitors are interconnected in such a way that to hold the 8-bit information. This is actual truth. Okay, so this is what I would like to stress in this case. Okay, so each bit is called as a cell, and each cell is designed with the help of the flip-flops in case of the static RAM. Each cell is designed with the help of the capacitor in case of the dynamic RAM. In order to hold the 8-bit information in a particular memory location, these flip-flops or the capacitors are interconnected in such a way that they are holding the 8-bit information. Okay, so that's it. So with this, the memory devices concept is over. But when you are going to interface your memory devices to the microprocessor, when you are going to interface your memory devices to the microprocessor, then the microprocessor is seeing the information, that is the memory devices, in the memory banks format. Okay, so microprocessor treats your memory devices in the memory banks format. In the memory banks format. So memory banks format na. So what exactly that particular memory bank means? Under the interfacing memory devices, we are having the memory devices as well as the memory banks. What is the memory bank, and how they are going to be used is a question. So here, uh, let me take one simple explanation for your convenience. I'm not going to take much time for this. A simple explanation. So let us suppose I'm having the 4-bit combination. Or otherwise, I can say that there is a 4-bit address. We are having the 4 address lines. 4 address lines means how many combinations we are going to get? Obviously, we are going to get the 16 combinations. 16 means it is a little bit difficult, right? I'll take the 3. Okay, let us suppose we are having the 3 address lines. How many locations are there? 3 address lines means we are going to get the 8 memory locations. We are going to get the 8 memory locations. I'm naming those addresses as A2, okay, A1, A0. I'm calling these as address bit positions. So address bit positions A2, A1, A0. We are having the 3 combinations. So the binary combination is going to be what? For the 3-bit, the binary combination is going to be the 0, the binary combination is going to be the 0, 0, 0. What I'll do is I'm not going to. These are the 3, right? So I'm just writing the 0, 0, 0. The 8-bit combination 0, 0, 1. Okay, 0, 1, 0. 0 double 1 1 double 0 1 0 1 1 1 0 triple 1. Okay, triple 1. These are the bit positions. Okay, this is a A2 bit position, this is a A1 bit position, and this one is going to be the A0 bit position. Okay, if you take this one, how many combinations we got? 8 combinations are there. Starting from where? Starting from the 0 to, starting from the 0 to, sorry, starting from 0 to 7, starting from 0 to 7. Okay, so here if you see this one, yeah, let me take the numbers also in decimal format. This one is going to be the 0, this one is going to be 1, 2, 3, 4, 5, 6, 7. Okay, so if you see this one, we are having the even and odd combination. When we are having the sequential number, obviously it is a group of even and odd number. Okay, now. So if you take this one, 0 is a even number, 2 is a even number, 4 is a even number, 6 is a another even number, 6 is a another even number, and 1, 3, 5, 7 are the odd numbers. 1, 3, 5, 7 are the odd numbers. 0, 2, 4, 6 are the even numbers. So if you see this one, whenever we are having the A0 position as a 0, A0 bit position as a 0, whenever we are having the A0 bit position as a 0, A0 bit position as a 0, at that time only, or I can say that whenever the A0 is a 0, then that bit combination is a even number. Whenever the A0 is a 0, that bit combination is a even number. Whenever the A0 is a odd, whenever the A0 is a odd, 1, binary 1, then we are having the odd combination. It is a odd number. Okay, it is a odd number. Are we clear? Okay, so means in any address combination, in any address bit, I'm just taking the 3 address lines now. If you are taking the 20 address lines also, whenever the A0 bit position is 0, at that time that address combination is indicating the even number. Whenever the A0 bit position is a 1, that address combination is indicating the odd number. Okay, now so that bit combination, but here we are having the A0 for the 3-bit combination. If the A0 is a 1, then it is going to be the odd number. Wherever you are having the A0 as a 1, the rest, whatever the bit combination is there under the A0 as a 1, then that is going to be the odd number. That is going to be the odd number. Whenever the A0 is a 0, at that time that bit combination is giving the even number. Even number. So if even if you are taking the 20-bit address line, at that time also, if the A0 is a 0, then it is a even address combination. If the A0 is a 1, then it is a odd address combination. So based on the A0 position only, based on the A0 position only, they are commenting that whether the memory is a even memory or whether the memory is a odd memory. Okay, they are commenting that whether the memory is a even memory or whether the memory is a odd memory. Okay, if the A0 bit position is 0, if the A0 bit position is 0, then that memory is a even memory. If the A0 bit position is a 1, then that memory is a odd memory. Remember that point. So based on the A0 bit position only, the microprocessor is treating the memory devices into whatever the memory you are interfacing to the microprocessor, that is splitting into the two banks format. One is a even bank and another one is a odd bank. One is a even bank and another one is a odd bank. Okay, so whatever the device which is having the A0 bit position as a 0, then it is giving the even bank. And whatever the device which is giving the which is using the A0 bit position as a 1, then it is called as a odd bank. It is called as a odd bank. Are we clear so far? Okay, now. But if you are taking a particular memory device, never think that this particular memory device is always giving the even addresses. It is not like that actually. So this memory device is giving the even as well as the odd address. It is a sequential number. But depending on the address line, which is a A0 bit position, we can differentiate. We can make one of the memory device as a even memory, and we can make one of the memory as a odd memory. So that is going to be decided with the help of the A0 only. That is decided with the help of the A0. Okay. So just remember that point. So after that you will come to know that how to assign the even addresses only and how to assign the odd addresses only. Uh, you will come to know that particular point, but just remember that whenever the A0 bit position is a 0, we are getting the even combination. Whenever the A0 bit position is a 1, we are getting the odd combination. We are getting the odd combination. Okay, that is the odd number. Okay, so if I'm calling one of the memory devices as even memory, means don't think that all the memory locations are even only. It is made as a even. Actually it is having the sequential memory only, but it is made as a even based on the A0. One of the memory device is called as a odd memory device, means it is made as a odd with the help of the A0. But if you take the individually without considering the A0 combination, if you take the individually, they are the sequential memory locations. They are the sequential memory locations. Now, let's go back to our memory banks concept. Let's go back to our memory banks concept. In the memory bank, in the memory bank, what is the maximum memory that can be accessible by our what is it 8086 microprocessor? Na? 8086 microprocessor. What is the maximum memory that can be accessible by 8086 microprocessor? Any idea? Okay. How to calculate that one? Any idea? Hmm. Okay. So as the microprocessor is supporting the 20-bit address, as the microprocessor is supporting the 20-bit address bus, 20-bit address bus, we are able to access the 1 MB memory. The microprocessor is able to access the 1 MB memory. I'm assuming that this 1 MB memory is equally split into two parts. Okay, now 2 per 20 is equally split into two parts. Okay, so 1 MB means 512 KB, 512 KB, plus another 512 kb, another 512, 512 kb and another 512 kb. So here I'm assuming that this 1 MB is split into, if you take this one, it is going to be 1024 1024 kilobytes. 1024 kilobytes means it is going to be 1 MB. 1024 kilobytes means it is going to be 1 MB. Okay. So here I'm assuming that in the market, I would like means I'm designing one what is that microprocessor based system, and I would like to interface the memory device. I would like to interface the memory device. This is the other way of explanation. So I'm trying to interface the memory device with the microprocessor. What is the maximum memory that can be accessible by our 8086 microprocessor, which is a 1 MB. But unfortunately, I'm assuming that in the market we are not having the 1 MB memory devices. We are having only the 512 KB memory devices. We are having only the 512 KB memory devices. Okay. So these two 512 KB memory devices are interfaced to the microprocessor in terms of Banks format. In terms of Banks format, with the help of the A0. So I'm with the help of the A0 bit position, I'm going to make one of the memory device as a even memory, and one of the other memory devices called as a odd memory. One as a even memory and another one is a odd memory. Okay. How we are going to do that one is a question. So let us see this particular diagram. In this diagram, this memory device is a 512 KB. This memory device is a 512 KB, and this memory device is a another 512 KB. What is the maximum memory that can be accessible by 8086? It is a 1 MB, and 1 MB in the market I am assuming that we have only the 512 KB devices. So this is a one 512 KB device, this is a one 512 KB device, and this is a another 512 KB device. So what are the control signals which are there in the memory device? We are having the read operation, where we are having the read signal, we are having the write signal, we are having the chip enable signal. I'm not considering the rewrite signals over here. I'm considering only the chip enable signal. So means for this particular memory device, we are having the chip enable signal, which is a CE bar. And for this particular memory device, we are having the another chip enable signal, which is a CE bar. I'm not considering the two more control signals, which are read and write signals in this diagram. Okay, because I would like to show that how I'm configuring one of the memory device as a even memory and another memory device as a odd memory. So here, this chip enable signal is there. This chip enable signal is connected to the A0 pin. I'm connecting the A0 pin. That is a we are having the 20-bit address line. So if you see this one, I think all of you able to see this, right? So we are having the 20-bit address bus. In this 20-bit address bus, as we are having the 512 KB devices, in order to access the 512 KB, we require only the 19 address lines. We require only the 19 address lines. So here, those 19 address lines are nothing but A1 to A19. A1 to A19 are the 19 address lines, and A0 is taken as a separate one, because I would like to make one of the memory devices a even memory and another one is a odd memory. Now, I am taking the A0 bit position, A0 line to enable this particular memory. Means whenever the A0 is a 0, at that time only this memory device is going to be enabled. If the A0 is a 1, this one is going to be disabled. This one is going to be disabled. Now, when the A0 is a 0, at that time this one is enabled now. No problem at all. When the A0 is a 1, this one is disabled. This one is disabled means this one is going to be enabled by the help of the BHE bar signal. I told you that during the explanation of the pin diagram, BHE bar signal is a bus high enable signal, which is used for indicating whether we are having the valid data on the higher order data bus or not. Higher order data bus or not. So here we are having the data bus now. The data bus which is supported by the 8086 is a 16-bit data bus, and that 16-bit is split into two parts. One is the higher order data bus and another one is the lower order data bus. One is the higher order data bus, another one is the lower order data bus. The higher order data bus is nothing but the D15 to D8. Lower order data bus is nothing but the D7 to D0. D7 to D0. So this one is going to be enabled with the help of the BHE bar signal. This memory device is enabled with the help of the BHE bar signal, and this memory device is enabled with the help of the A0 signal. With the help of the A0 signal. So as we have seen few minutes back that whenever the A0 bit position is 0, it is giving the even combination. So obviously when the A0 is connected to this one, this entire thing is giving the even locations. Okay, when the A0 is a 1, this one is going to be disabled now. When it is disabled, obviously this one is going to be enabled by the BHE bar signal. So that's why this memory is giving the odd addresses. This memory is giving the odd addresses. Let us see the slide continuously. So here, as I told you that this memory device is giving the even addresses only. So even addresses means 0, 2, 4, 6 and so on. CE. All these are the even addresses. And this one is giving the odd addresses now. So that's why it is called as a 1, 3, 5, 7 and so on. Again, I am saying that if you are taking a particular memory device, it is not giving only the odd addresses and it is not giving only the even addresses. Don't get confused that one. We are making the addresses, one of the memory devices, even address and the odd addresses with the help of the A0. Just remember that point. Never think that a memory device is giving only the even addresses and a memory device is giving the odd addresses. Actually, it is having the sequential memory locations. Means odd as well as the even combinations. Odd as well as the even combination. Okay. Now, what I'll do is this particular even address bank is called as a lower bank. This particular memory device is called as a lower bank because the starting number is going to be the 0 now. So it is called as a lower bank. And the odd address bank is called as the odd address memory is called as a upper bank. Even address memory is called as a lower bank. Odd address memory is called as a upper bank. Now, as I told you that the A0 is used for A0 is used for this lower bank memory to enable the chip enable signal of this particular memory device, and BHE bar is used for enabling the chip enable signal of the upper bank. And one more thing is the lower bank is going to be connected to the lower order data bus. The lower bank is connected to the lower order data bus. Okay, so we are having the lower order data bus as well as the higher order data bus. Now lower order data bus is connected to the lower bank, which is nothing but the even bank. And here this particular memory size is how much ma? 512 KB na. So in order to access the 512 KB, how many memory locations we require? How many address lines we require? 19 address lines, and that's why the address lines which are coming from the microprocessor A1 to A19, they are connected to to this particular device. Okay, and A0 is not used because we require only the 19 address lines, and A0 is used for differentiating which memory device is a even bank and which memory device is a odd bank. Whenever the A0 combination is a 0, it is a even bank now. So during that time only it is going to be enabled. During that time only it is going to be enabled, right? So the next case is upper bank. So in the upper bank also, upper bank size of 512 KB na. In order to access the 512 kilo memory locations, how many address lines we require? 19 address lines. So A1 to A19 address lines coming from the microprocessor, they are connected to this particular memory device, and A0 is not connected. A0 is not connected, but the chip enable signal is connected to the BHE bar. And one more point is upper bank is connected to the higher order data bus. Upper bank is connected to the higher order data bus. So based on this, what is the use of the BHE bar? BHE bar is showing the whether the D8 to D15 is having the valid information or not. D8 to D15 lines are having the valid information or not. Whenever the BHE bar is disabled, obviously D8 to D15 lines are not showing the D8 to D15 lines are not what transferring the data. That is a means reading the data or writing the data. They are not participating in the data communication because when the BHE bar is a high, obviously this signal is going to be high. When this signal is high, then this device is going to be disabled. When this device is disabled, then obviously D8 to D15 is not performing any kind of operation. Means these are the this particular data bus is in the tri-state mode. Okay, now. So we are having the lower bank and the upper bank. So 1 MB memory is divided into two equal parts. One is the 512 KB, another 512 KB. One 512 KB is called as the lower bank, another 512 KB is called as the upper bank. Lower bank is called as the even bank. Lower bank is called as the even bank. Why it is called as the even bank means whenever the A0 is a 0, at that time only that bank is going to be enabled. So that's why it is called as the even bank, because A0 combinations, A0 is a 0 means it is an even combination. So the A0 bit position is connected to the CE bar now. Because of that, this bank is called as the even bank. And A0 is not connected to this one, and BHE bar is connected. Means when the A0 is a 1, at that time this signal is going to be enabled. Oh, sorry, this bank is going to be enabled based on by using the BHE bar signal. So that's why it is called as a odd bank or the upper bank. So lower bank is connected to the lower order data bus, upper bank is connected to the higher order data bus. Okay, higher order data bus. This is the memory bank concept. Let us suppose I would like to perform the read write operations. would like to perform the read operation or write operation on the even bank or on the odd bank, either in the 8-bit format or in the 16-bit format, either in the 8-bit format or in the 16-bit format. So for that we are having one table. So don't get confused with this table. If you would have realized the concept called as a direct memory address concept in the 8086 microprocessor, then you can realize this one. So what we do is we'll see this particular table explanation in the next class, because time is exceeded, the size is going to be more. So what you do is, before the next class, you just go through the direct memory access. We have seen the addressing modes now. What you do is, under the addressing modes, you just go through the direct memory access addressing mode. Okay now. Okay now, direct memory access addressing mode, or I can say that it is a direct addressing mode. Direct memory addressing mode, or the under the memory addressing mode we are having the direct memory addressing mode. Direct addressing mode, you simply go to the direct addressing mode in 8086 microprocessor addressing modes, so that you can easily realize this particular what is that table, this particular table. Sima, the memory banks concept is important long question. As per your semester exams, the memory banks concept is very important question. Okay, now very important question. So what you do is, before the next class, you go through the direct addressing mode in 8086 microprocessor. Okay, that's all for today's class. If you're having any queries regarding this particular topic, you can raise in the WhatsApp group or in the YouTube channel itself. You can comment in the YouTube channel.